So first of all, let's figure out how do we do the first part. How do we sample Ti and Vi? So let's just use one of them. Let's say Vi. Okay. So how to sample from a triangular distribution? So the triangular distribution is the following PDF. It's like that, right? No, actually the other way. So the nominal is 220, maximum is 250, minimum is 210. All right. So before we talk about how to sample that, what is the value at the top? How do you determine what's actually the value of the PDF at the top of the triangle? Yes?
You want the area to be 1.
Yes, you want the area to be 1.
1/2 times 40 times the top value.
Yeah. So you can see the base of the triangle has a width of 40, right? You want the width times the height to be equal to 2. So the height should be what? 0.05. Yeah, okay, very good. So I'm going to teach you 2 different ways of sampling from this triangular distribution. These 2 ways are 2 of the primary ways to sample from any known distribution. So the first approach is based on this PDF. So one, let me call the PDF based approach, also known as the acceptance rejection approach method. Okay, the second is actually not based on the PDF but based on the CDF. So what is the CDF of this function? Let me draw. X is still the delta V, right? 20 to 50. So what's the CDF of this function? Yeah, so because the triangular distribution are piecewise straight lines, the CDF, which is the integral of the PDF, would be piecewise parabolas. So you would start, so again CDF is equal to the integral of the PDF, right? You start from 0 at 220, at 210 because the PDF is 0 before that. You get to 1, right, at 250 because that's the entire mass of the PDF. But in the middle, what do I know, right? So I know I'm going to have a piecewise parabola. And particularly at this end of the parabola, my slope should be the same as the height of the PDF, which is 0, right? So I should have a 0 slope over here. Also, when I'm over here, again, I should have a 0 slope. And in the middle, the value of the CDF should be the same as what? Yeah, it should be the same as the area on the left, which is 10 times 0.05. It's it divided by 2, which is 25%, right? So at this point, I should get to 0.25, and I have a parabola that goes up to this point. I have another parabola that goes down over here, right? So that's kind of the CDF I have. You can probably just compute from this what's the analytical form of these 2 parabolas. But anyway, it's a piecewise parabola. You can figure that out for any triangular distributions. All right. So the CDF-based method is the second method I'm going to teach, and it's called the transformation method. Okay, so let me actually have you try to do this method yourself, and we can split into groups and you can choose which one to perform. But let me just describe the simple idea behind each of them. Okay, so on the left-hand side, if I know the PDF, suppose I have, it's actually not too difficult to imagine. If I know the PDF of a function or of a distribution, but the PDF, the form of the PDF is so complicated that it doesn't have an analytical integral. So the CDF actually is very hard to compute. Then I want to sample based on the PDF, right? The idea is, instead of sampling from this PDF, I'm going to sample from a PDF that dominates this PDF, or a PDF that is higher everywhere than this PDF. So in this case, for the case of a triangular distribution, or actually any distribution with a finite PDF and finite width, it's possible to choose a uniform distribution that kind of looms over this PDF like this when you scale it by a finite number. Okay, and then I sample from this overshadowing distribution. If I get a particular sample, then I'm going to either accept the sample or reject the sample based on the relative height of the red PDF and the blue PDF. So this is in some sense equivalent of saying, if I get within a particular sample, then I look at the PDF I want to achieve. If the PDF has a low probability density at that point, I'm more likely to reject it, right? Because it's more likely to be lying in this proportion. And if I actually sample at a high point in the PDF, I'm more likely to accept it. So that's the PDF-based method, acceptance rejection method. All right. In another different way to think about it, instead of sampling this one dimension, I'm actually going to be sampling these two dimensions, right? And the sample that lies above this PDF is all rejected. The sample that lies below the PDF is all accepted. So that's this method. The CDF-based method actually requires a little bit more manipulation than deriving the CDF. It requires the inverse of the CDF function. So not only you have to actually derive the quadratic form of these two piece quadratics, you actually have to solve two quadratic equations to figure out the solution of these two quadratic equations, because it's the inverse of these quadratic functions you actually need. So this method, you are going to be effectively speaking, instead of sampling the x-axis, you are sampling the y-axis. You are sampling the distribution over here and then map it, right, to the distribution over here. And you can see from here that whenever you have a very shallow CDF, you are mapping. What does shallow mean? Shallow means you are mapping a small region in the y-axis into a bigger region in the x-axis, right? What that means is that, yeah, the PDF is actually low in the x-axis because it's very unlikely for you to get a sample in the y-axis that lies in a very narrow region. While the PDF is steep, that means you are mapping a relatively large region in the y-axis into a relatively small region in the x-axis. And that's the point where the PDF is high, because you are grabbing a lot of samples in a large region in the y-axis and focusing that on a small region in the x-axis. All right. Okay. So that's. I think I have described the entire two methods. Anybody have questions? Yes?
So can you elaborate more on what the acceptance or rejection criteria is in the PDF case? Like, I guess, how do you differentiate between, in the PDF case, how do you differentiate between that and like the same triangle in the same area, but like it just like flipped to the other side.
Flipped to the
Or
other
like
side.
biased to the other side than to the right rather than the left. Like how?
I see. Okay, so can anybody here answer that question for me? So I think his question is if I have a PDF that is like that, how would the algorithm be different?
But don't you define the
So you
position and the
not like as area data.
Yeah.
Like if it's hard to keep, you cannot have this situation.
Yes. So can you just describe to Fasal that if I have the red PDF versus the green PDF, how would the algorithm compute or accept or reject the samples in a different way?
So is the rejection and acceptance like based on the area, or are you just doing it per like every strip of like every depth of the value? Are you using the acceptance and rejection?
What do you think makes more sense?
The second one.
The second one, right?
Yeah.
So I'm just going to based on the value of the PDF at that sample value. Okay, so let me just go to MATLAB and do this very quickly.